Welcome back to Simple Quant. Today we will explore St. Petersburg paradox, which is an easy probability question often seen in quantitative finance interviews. The question reads as following. Suppose you are offered to play a game where you flip a fair coin until you obtain a heads for the first time. If the first heads occurs on the nth flip, you are paid out 2 to the n dollars. What is the fair value of this game? What is this question asking? So the question is asking for the fair value of the game, which is how much would you pay to play this game? And this is a similar concept as expected value. In fact, they're the same thing. So imagine the fair value of a game. You can think about it like this. If you were to expect to win $5 from a game, the max you'd pay to play for the game is $5. In this case, we're trying to figure out what's the max amount we're willing to pay to play this St. Petersburg coin flipping game. So let's calculate the expected value. The expected value is found using this equation, which is the sum of the value of an event occurring times the probability that that event occurs. And I'll walk you through how that looks for this problem. So in this game, the expectation of the game, this is the expectation, will be the sum of all the possible probabilities of events occurring and how much you would expect to make from each of these events. So for example, this one right here is the event that the first heads is on the first toss. And then this one would then be the expected value of the first heads on the second toss. And the way this is worked out is this is the probability of landing a tails or the heads on the first flip, and the probability that you get the first heads on the second toss is the first flip is a tails, which is 1/2, times the second flip is a heads, which is another 1/2. And then you multiply these by the value you get with that event occurring. So if we continue this, the expectation of the game then becomes, it keeps going with all these terms, as this is like the probability that you get the first heads on the third flip, this is the first heads on the fourth flip, and so on. And this is the general term where you get the first head on the nth flip. And as you can see, this general term simplifies to 2 over n times 2 over n, which is just 1. So your expectation of the game is just a sum of a bunch of 1s. And here we see that the expectation of the game is just a sum of 1s, but we also know that this term will always exist for any n. You can think about it like this. There's a very, very low probability that you get your first head on the 800th flip, but there still is a probability that that occurs. There is a scenario where you can flip 799 tails and then get 1 heads on the 800th flip. Thus, this term will always exist, and this sequence will continue on forever. Right here, we see that this will just be an infinite sum of 1s. So thus, the expectation of the game is actually infinity. The fair value of this game, the amount you'd be willing to pay for this game, is infinite. And this is quite paradoxical because there's a very high chance, 50% chance, you end up with only $2. But even in this scenario, you're willing to pay infinite money to play this game. All right, thank you for listening. I hope you enjoyed. Leave a like and subscribe. Thank you for listening.